Okay, so let's get started. Can people on Zoom hear me? You got a signal? Okay. Okay, great. So today we are going to continue to talk about transactions, right? So more specifically, we are going to talk about isolations and also how can we enforce isolation by holding locks. So on Wednesday, we started from this motivating example, right? We think about a scenario where there are two concurrent requests from a bank to actually withdraw money, right? And we look at this example, right? So if you are not being careful about how you mix all those instructions together, and you could cause a problem, right? So this is a very natural example, right? So for each of this group of instructions, right? So you have one common state inside your database system. And then essentially, right, you do these four things. You first read that state, you update the state, and you write it back. If you mix this instruction in a certain way, right, if you are running a bank, you are actually start to allow someone to actually withdraw more money than he has. So if you look at why this could happen, essentially we are missing a fundamental level of abstraction. That is, we need to tell the database system, this is actually a group of instructions. You cannot treat them separately. They belong to a single group. And more formally, and like what do we mean by something forming a group? We define these four different properties that we want out of a transaction. The first one is atomicity, right? Which essentially means that if you have a transaction, you run in the system, and if the system fails at any point in time, so when you reboot the system, you can only see two possible states. Either all the changes of the transaction is in, or none of the changes are in. You will never see something in the middle when you reboot your system. You will never have an inconsistent state. The second property is called consistency, which is essentially means that if you have a group of transactions, what this group of transactions do is going to transform database from a consistent state, precisely that's a state where all the integrity constraints are being respected, and then transform that into another consistent state. So third property is called isolation, which concerns the cases when there are multiple transactions running at the same time. Isolation essentially says that even though you have multiple transactions inside the system running at the same time, it is as if transactions are running one by one in the system. So those multiple concurrent transactions are isolated in some way. And the fourth property is called durability, which essentially means that once the transaction tells you, okay, I committed, and then no matter whether the system fail or not, after that, whenever you reboot the system, recover from the failure, right? So recover from the failure, you are going to still see the changes of the committed transaction. Once the transaction tells you I committed, you will never lose the changes from that transaction. So once we define the notion of groups of instructions, we can start to formally define the property we want from that group. And when you are using a database system using transactions, this is a contract between a system and its user. Essentially, once you define transaction, this is what I'm going to give you. And once we define that formally and precisely what we want out of a transaction, we can think about how to enforce it in a systematic way. So in this lecture, we are going to talk about two things. The first one, we are going to define even more formally some of those properties. Because if you look at what we have before, as you will see, some of those definitions are not even that precise. For example, isolation, right? We talk about one schedule being serializable last time, right? So we say, yeah, so like you have one schedule, which is one specific way you can mix all those instructions. We want them to be the same as some serial schedule. That's not precise at all. What do you mean by same, right? Because there are so many different ways you can define equivalency between two states, between two schedules. So we are going to make them even more precise. And second, we are start to think about how to enforce some of the properties. And in this lecture and also next Wednesday, we are going to spend 2 lectures talk about isolation. So there are different ways you can enforce isolation, and we are going to talk about one specific way today, and we are going to talk about another one next week. Today, we are going to talk about how to enforce isolation by holding locks. Okay, now let's define a transaction and the property a little bit more precisely. So we think about database as a fixed set of named data objects. Okay, so we don't think in the level of tables or tuples. We think in the level of objects. There are a whole bunch of objects. Each one of them has a name. So in practice, transaction can create new objects, okay? But here, let's assume transaction only read and write objects. They do not create new objects. So a transaction is a sequence of read and write operations. So essentially, when we have this notation, right, we say, yeah, you have this object inside database. I read that from database into a variable A. When you have this, right, you can also write. You can say, yeah, so I have this object B. I want to write a new value. One assumption that we are making is the moment you issue this write instruction, and the moment database actually run it, the changes are reflected inside the database. Okay, so that's one assumption that we have. Essentially, when another read instruction happens after write, it's going to see the updated value. Okay, so write are being reflected immediately. A transaction starts with begin and could end with 2 different possibilities. You could either commit, tell the database, okay, reflect all the changes, or you could abort. Say, okay, I want to cancel this transaction, just roll back. I don't want any of the changes you made so far inside the system. I'm going to cancel this transaction. So if commit, all changes are saved. If abort, all changes are undone. So that is like this transaction never happened at all. So if you think about who is going to issue abort, the most natural answer would be the user could do that, right? You are typing those SQL queries, and at some point you say, I don't want to do that anymore, I just abort. It's fine. And sometimes abort can also be issued by the database system. It's sometimes going to force some transaction to abort, and we are going to see one of those cases actually toward the end of today's lecture, where the database is going to issue an abort statement for some of the transactions. So it can happen both ways. Now let's look at one example. Okay? So let's say we have 2 transactions, T1 and T2. So they look like this. T1 is very simple. Okay? So I have one data object A. I read it and load that into a variable T, and I increase that by 100. That's the second instruction. And then I write it back. Then I read B, increase 100, write it back. T2 is doing something very similar. Okay, it's read A, multiply by 2, write it back, read B, multiply by 2, write it back. It's as simple as this. So first one, let's try to reason a little bit about consistency, right? Because each transaction needs to be consistent. Assuming we have one integrity constraint inside the system that is A equals to B. Okay, and you know how to specify that now. So assuming it's A equals to B, this is my integrity constraint. So first one we can see, both transactions are consistent. How can we reason about that? Well, you think about what would happen, right? So in the beginning, I have a database instance where A equals to B. Right? And your input is a consistent state. After you run T1, as long as in the input A equals to B, in the output A also equals to B inside database. So T1 is consistent. Similarly for T2, right? Your input A equals to B, you multiply both by 2, the output must be the same. So both transactions are consistent, so we are pretty happy about it. Right? So they transform a consistent database state into another consistent one. When we say a schedule, is actually a specific way of mixing these instructions together. So there are some schedules that are just zero schedule. That is, you run one transaction, then you run the other one. This is the one zero schedule that you run T1 first, and then you run T2. If you think about what's going to happen inside the database, let's try to go through this together. It's a very simple example, but let's try to make sure we are on the same page about what read and write is actually trying to do. So assuming your database starts from a state that A equals to 10 and B equals to 10. After running the first instruction from T1, your database state is stay the same. Okay, we are going to use that notation. Okay, it stay the same. Seems like the same as before, 10 and 10. And then you increase T by 100. The database state is still the same, okay, because you do not change it. So the moment you write, you are going to have a new database state, okay, after you issue this write operation. And then when you read it, right, now the T has a value of B equals 10. You keep doing this, right? So once you write, you change the database state. And then T2 read, okay? Now T2 going to read the new value of A, which is 110, multiply by 2, write it back. Then read the new value of B, multiply by 2, write it back. If you run this schedule, you are going to transform the database from a state where A equals to B equals 10 to another state, A equals B equals to 220. There could be multiple zero schedules, right? You could run T1 first, you could run T2 first. If you run T2 first, right, you are going to have something like this, right? So you're going to have 10 and 10. After T2, you have 20 and 20, right? After T1, you have 120 and 120. If you put this side by side, as we can see, even you have the zero schedules, right? They could give you different result in the end. From the eye of a database system, we are okay. As long as you output either one of this, we will be happy. We are not going to enforce a specific order of how these transactions are being executed. As long as they are zero, we are happy. Okay? So we want whatever schedule we have, output something that equals to one of these two. We say a schedule, a specific way of mixing instructions, is serializable if that schedule gives you the same answer as some zero schedules. So let's look at this very specific way of mixing instructions. I run the first 3 instructions of T1 first, then I run the 3 instructions of T2 first, so on and so forth. If you do this, what would I get? Right? My input is still 10, 10, right? After the first 3 instructions from T1, right, my A equals to 110, my B still is 10. And then after I run the T2 part, right, so I get 220 and 10, right? So, and then I run the B part from T1, then I run the B part from T2. So as you can see, even though you are changing the order of execution of those instructions, at the end of the day, you get the same thing. You get 220, 220, right? The same as some zero schedule. If that is true for your schedule, that you get the same answer, same in the sense that all the database object is in the same state. A is 220, B is 220. If that is true, then we say they give you the same answer. Okay? And then, if you can find a zero schedule that gives you the same answer as your schedule, we say that schedule is serializable. This is just one example of a serializable schedule. But not all the schedules are serializable. Okay? So this is another example that's actually not serializable. I run the first 3 instructions of T1 first, then I run the whole T2, then I finish up T1. If you think about the evolution of the database state, right? In the beginning I have 10 and 10. After I run the first 3 instructions of T1, I get 110 and 10, right? And then I run T2. I'm going to multiply A and B by 2, then I have something like this. Then I finish up T1. I'm going to read B, increase by 100. At the end of the day, I'm getting 220. and 20 and 120. If you look at these two database states, first one, I mean, this schedule, after you run this, doesn't even give you a consistent state, right? So my integrity constraint was A equals to B. A doesn't equal to B anymore, right? So there's no way you can find a serial schedule that give you that. So this is one example schedule that's actually not serializable. So far, it's very natural, right? Any questions about this? It's very natural. Okay. The next example is going to get a little bit tricky. Because if you think about how can we decide a transaction is serializable or not, what should we look at? I mean, I don't really want to run it to decide whether it's serializable or not. Can we decide whether a transaction is serializable by just looking at I/O pattern? That's one fundamental question that we are kind of curious about. I do not want to run the transaction. I want to look at it, or have a machine automatically look at it, and try to decide whether it's serializable or not. Can I just look at the I/O pattern? Oh, you read A, you write A because of a conflict, so it's not serializable. Can we do that? So it's actually one interesting thing is the I/O pattern itself does not fully decide serializability. That you need to look at both the I/O and the computation. So this is one example. In this schedule, I have exactly the same I/O pattern, right? I have the first part of A, I read A, write A. My read and write pattern are exactly the same. The only difference is I'm changing the computation in T2. Instead of multiply that by 2, I increase the value by 200, for example. If you have these two transactions, this schedule has the same I/O pattern as the previous one. Only the computation is different. If you think about what it's going to do to your database, in the beginning you have 10 and 10 as a state. After the first part of T1, you got 110 and 10. After T2, you have, for example, 310 and 210. And then you finish up T1, you have 310 and 310. If you look at this serial schedule, right, so it's very easy to see, it's going to give you the same state. So this is one example that you have the I/O pattern as before, but because your computation is different, you are kind of become lucky, right? You are very lucky they are actually serializable. The result is the same. This is a serializable schedule. So as you can see, whether a schedule is serializable or not depends on two things. Depends on the I/O pattern, and also depends on what the computation that this transaction is trying to do. And also, it's also going to depend on the state of the database. So that is not something we like. Because if you think about this, if whether a transaction is serializable depends on all these three things, the only practical way I can actually test whether a schedule is serializable or not is by running it and look at the result. We don't want that. Ideally, the thing that we want is to have something that I just looking at it, look at the schedule without running it, without thinking about what is the state of database is in, and then I can decide whether it's serializable or not. So because of that, we want to introduce a different notion of serializability called conflict serializability. So what do we want to do, right? So we see the I/O pattern itself, the arrangement of read and write, does not fully decide serializability. It depends on the computation, depends on the database state, which are very hard for a system to analyze automatically. What we want is a stronger notion than serializability. And what we want is something that we can fully test by just looking at the I/O pattern. Okay? So because if you can have this notion, it's going to be easier for the database to handle because it does not require the database to understand the computation itself, which is very, very hard to do. So what is the high-level idea of this? essentially we want to define some notion which is strictly stronger than serializability. That is, if the something is conflict serializable in that notion, you can imply it's going to be serializable, so you are going to be safe. But if something is serializable, it doesn't necessarily imply conflict serializability because that's strictly stronger. That is what we want. The high-level idea is by thinking about those conflicts of I/O patterns. For each pair of operations, we try to define certain mode of conflicts. And we try to say something is conflict serializable when for each pair of those operations, there's no conflict at all. That is what we want to do. So essentially, we can define 3 different types of conflicts. First one, if you talk about a pair of operations within each transaction, they're always conflicting with each other in the sense that you cannot swipe their order. That's how we think about it. Okay? If you have a pair of operations, if you can swipe their execution order, then we say they are not conflicting with each other. Okay? When you have the same transaction, take 2 operations, you cannot swipe the order, right? I mean, that's very natural, right? I define a specific way for you to run it within a single transaction. You cannot say, okay, I want to run the second instruction first, right? So you take 2 pairs of operations inside the same transaction, they're always conflicting with each other. If you take 2 operations, O1 from T1 and O2 from T2 from different transactions, so they are conflict if one of them is a write to the same location. And conflict serializable, this notion, essentially we try to reason whether we can translate a schedule into a serial schedule with a sequence of swipes of adjacent actions that are not conflict with each other. So this definition is very abstract at this moment, but it's going to become very concrete. So one thing is like when we talk about serializability, right, we, so far, like at least in this course, we only worry about those committed transactions, okay? Okay, so there are 3 different types of conflicts between operators of different transactions. There's a read-write conflict, there's a write-read conflict, there's a write-write conflict, okay? So let's look at one example about what do we mean by 2 operators being in conflict with each other. Now let's look at this I/O pattern, okay? T1 read A, then T2 read A, T2 write A, T1 read A. We can look at those pairs of operations. So let's look at this pair, okay? So T1 read A, T2 read A. We see there's no conflict between these 2 operators. Why? Because if you think about this, if you swipe the order, instead of running T1 read first, you run T2 read. It's fun, because they are reading the same thing, right? You could swipe the order and get the same thing. Make sense? If that can happen, we say there's no conflicts between these 2 operators. But look at this pair. You have the read from T1 and write from T2. Can we swipe the order? That we cannot, right? Because if you swipe the order, you are going to have very different behavior from that schedule. When you cannot swipe the order to get the same thing, we say there's a conflict between this pair of operators. So what is the problem when there's a conflict here? So there's a problem there is because when you have read A and write A, if you read A again in T1, you have non-repeatable read. If you remember what we talked about on Wednesday, right? So that gave you a behavior that's not serializable at all. So we do not really want that type of thing. So essentially, assuming we swipe the order, okay? We swipe the order of read A and write A, that conflicting operator. Then you will not have this non-repeatable read. If you do not swipe the order, you are going to have non-repeatable read for this thing. That is why when you swipe them, you get a different result. Okay? When you can, that's a high-level idea. We try to define those different pairs of conflict operators, and those are defined as those pairs that you cannot swipe. Okay? So another thing, if you look at the two read, right, you can swipe. The moment like you swipe them, you get the same thing. So this is intuition behind the conflict serializability. We try to, by just looking at this I/O pattern, and try to have some operation you can do on the I/O pattern, such that you know you will get the same thing. Another type of conflict is this write-read conflict. So it's actually concerns about this pair of operations. That is T1 write A, and then T2 read A. Can we swipe the order? Right here we run the write first, and then we do read. Can we do read first and then do write? Will you get the same thing? So clearly no, right? So by just thinking about why they are going to give you different, is essentially assuming T1 abort in the end, right? So in this case, T2 is going, so in this order, T2 is going to read a value that actually doesn't really exist in that database. Because once you abort T1, you need to roll T1 back, but T2 is reading from T1, that will cause problem. But on the other hand, assuming you swipe them, okay, you run the read from T2 first, then you do the write from T1, you will not have this problem, right? So and that is why, right, so swiping them will not give you the same result. So similarly, there's this write-write conflict between these two operators, right? So the way to think about it, why you cannot swipe them, right, is assuming you have another operations. In T1, you write B, right? So if you, in the current order, right, you are going to actually introduce some notion of inconsistency, right? So assuming both of the, like within T1, right, your two writes to A and B is going to satisfy some constraint, like A equals to B. In T2, you could have A equal to B, the same thing. But once you have write A from T1, you have the T2, you have the write B from T1, you could introduce inconsistency between these two values. But on the other hand, if you swipe them, right, you are going to have a different behavior. So essentially, we define these three different notions of conflicts between pairs of operations. The HighLevel intuition is they actually define the ways that swiping two operators can cause inconsistency during concurrent executions. We say two schedules are conflictly equivalent when the following hold. That is, they involve the same action of the same transaction. Okay? Second, every pair of conflicting actions is ordered in the same way. If that is true, we say these two schedules are conflict equivalent. Intuitively, it means that because I'm respecting all of those orders of conflicting operators, I'm not swiping any of those conflicting operators in these two schedules. Okay? So they will give you the same result that I know. Intuitively, right, so these two schedules will have the same set of conflicts. So you are sure they are going to give you the same thing. And we say a schedule is conflict serializable if it is conflict equivalent to some serial schedule. If you look at this definition, it's different from serializability. We say a schedule is serializable if it gives you the same result as some serial schedule. And we say a schedule is conflict serializable if it's conflict equivalent to some serial schedule. To deciding whether a schedule is conflict equivalent to another one, you do not need to run it, because that only relies on the I/O pattern. So the one way to test it, there are two different ways to test it, but one test it, whether a schedule is conflict serializable, is to see whether you can translate that schedule into a serial schedule with a sequence of non-conflicting swipes of adjacent operators. Let's look at one example. We have this schedule. Okay, I have read A, write A from T1, read A from T2, read B from T1, write A from T2, so on and so forth. I have this schedule. Is this conflict serializable? What do I want to ask? Okay, whether they are conflict equivalent. Okay. Oh no, sorry. Oh yeah, so whether they are conflict serializable. Okay, yeah. So that is the question I want to ask. How to do it? The way to do it is you can swipe the order of adjacent non-conflicting operators. That we know, right? You can swipe the order because there's no conflict, so swiping the order will not change the result. For example, I could take these two operators, read A from T2, read B from T1. I know there's no conflict because they are both read. I can swipe the order. I can do the read B from T1 first and read A from T2. Okay? These two will give you the same result. Like no matter what database you have, no matter what computation you are doing within these two transactions, these two schedules you know will give you the same result. And then you know these two are conflict equivalent. And the second thing to do, you can take this and then you continue to do this swipe. Once you can do is, okay, can I swipe this pair? No, I cannot, right? Because, because they are conflict with each other. I know if I swipe the order of these two operators, I'm going to have, and potentially, have a different result. So once you do this, oh, sorry, it's too early in the morning. Sorry. Okay. So these two operators are not conflict with each other because they are writing to the different location. Okay. One is write B, another is write A. Okay. So there's no conflict between these two write to different locations. Make sense? So and you can swipe them because you know one is writing to B, another is writing to A, right? It doesn't matter the order because you are going to get the same thing in the end. So once you swipe them, you get the new schedule, and you know they are going to give the same thing. And you can continue to do this exercise. You can look at these two pairs. One is write B, another is read A. In this case, they are actually worried about different objects, right? So there's no conflict. So you can swipe them, so you get something like this. Essentially, you can do this sequence of swipes of non-conflicting adjacent operators to transform the first schedule into a serial schedule, where you run all the instructions from T1 first, and then you run all the instructions from T2. When you are able to do this, we say the schedule on the left-hand side is conflict serializable. And you can see why we want to have that notion, because every single time you swipe a non-conflicting pair of adjacent operators, you know you are going to get the same result. If you continue to do this and you reach something that's actually serial, you know these two things will give you the same result, no matter what database you have, no matter what computation you are doing inside this transaction. That's why conflict serializability is a stronger notion. Okay? It implies serializability. So now let's look at one example. I have these two very simple transactions. I have T1 and T2. I read A, and then T2 read A, write A, T1 write A. Is this schedule conflict serializable? Well, in this case, no, right? Because you cannot swipe non-conflicting adjacent operators to get a serial schedule. How can I know that? Because if you look at this pair, there's conflict. No matter how I swipe, the read will always be before the write. There doesn't exist a case I can swipe the order. There's conflict. And if you look at this pair, there's also conflict. You also cannot swipe. Because of this, there's no way I can swipe adjacent non-conflicting operators such that I can put the two instructions from T1 together. And because of this schedule is actually not conflict serializable. Make sense? Because there's no way I can swipe them to put T1 together. So there's another thing that's a little bit tricky, is we know how to swipe the order of read and write, right? But there's also the commit and abort, right? How can we swipe them? So essentially, the high-level idea is to have a write X in T1 and abort in T2. These two operators, read X and abort, there's a conflict if T2 updated X. The intuition is, right, for these two schedules, right, if you reorder the read and abort, they are going to lead a different value for read. So here's one example, right? So you have this read and you have this abort. So think about what would happen if you swipe the order. Okay? So in the first example, your read will come from T2, the write in T2. Okay? And the second example, your read will come from the value before T2, because before this read, T2 abort. You're going to roll back. So essentially, you cannot swipe the order of abort and read when you know the aborted transaction updated the same value. Makes sense, right? Because if you swipe, you're going to get a different thing. So similarly, right, if T1 write, T2 abort, right, it's the same thing, right? So essentially, you cannot change their order, right? So for a very similar reason as read. And when there's T1, there's write, and there's commit in T2, there's no conflict. Okay? You are able to reorder a write operation of X and a commit in another transaction. So here's high-level idea, right? So in this case, you have write A first, then you have commit, right? Looking at this pair and compare that with a schedule that looks like this. Right? So essentially, right, so there's no conflict. I mean, these two are going to give you the same thing. So essentially, just to recap, we have these two different notions of serializability. Something being serializable is defined by the equivalency of the result. You compare the database state. And something being conflict serializable is defined by whether you can swipe adjacent non-conflicting operations. To test conflict serializability, you never run the transaction. Okay? That is why we like it. So conflict serializability is strictly stronger than serializability, which means that if a schedule is conflict serializable, it's going to be serializable, but not the other way around. So conflict serializability only concerns about the conflict caused by read and write, not the commutation, not the initial state of the database, which is very hard for the database to reason. So most of the database system, if not all the database system, are trying to enforce conflict serializable, like serializability, instead of the serializability itself, because even deciding that is super hard. Any questions so far? Is this two different notions of serializability clear? Okay. Now let's try to look deeper into conflict serializability. Now we know what we want to do. How to decide it? Given a schedule, how can we decide whether it's conflict serializable or not? Well, there's a naive solution, right? Go back to definition, do the swipe. You try all the possible ways to swipe it, and you see whether you can reach a serial schedule or not. There's nothing wrong about it, but just very hard to do. So there's a much simpler way to decide conflict serializability. Essentially, you can actually build something we call a dependency graph. For each transaction, it becomes a node in the graph. We said there's an edge between T1 and T2, Ti and Tj, from Ti to Tj in the graph. If you have operator Oi in Ti, and you have an operator Oj in Tj that conflict with each other, and Oi appears earlier than Oj. If that happens in the graph, I have an edge from Ti to Tj, and I construct the graph, and I see whether there's a loop in the graph. So a schedule is conflict serializable if and only if its dependency graph constructed in this way is acyclic. So just look at one example. So here's one schedule contains 2 transactions. In the dependency graph, each transaction going to become a node in the graph. And what I'm going to do is by looking at every pair of operators in the schedule. For example, I look at this pair. I have write A in T1 followed by read A in T2. So these 2 operators, there's conflict, right? And then the T1 operator happens earlier than the T2 operator. So in the dependency graph, I'm going to have an edge from T1 to T2. If I look at this pair of operators, they are conflict because one is write to B, another is read from B. There's conflict. And the thing in T2 happens earlier than the thing in T1. In this case, I will have one edge from T2 to T1 because the thing in T2 happens earlier. And then I look at this graph. As you can see, there's a loop, right? T1 goes to T2, T2 goes to T1, there's a loop. When there's a loop in the dependency graph, we know this schedule is not conflict serializable. The intuition is clear, right? There's no way you can swipe them. There's no way you can actually swipe the JSON non-conflict operations such that you can put T1 together. Okay? So that is why whenever there's a loop, it's not conflict serializable. This allows you to do a whole bunch of other things to deal with multiple transactions. So let's look at this. You have 3 different transactions, and with this very specific schedule. In the dependency graph, you are going to have 3 nodes. Each transaction becomes a node. And then the thing you are going to do is you're going to look at every single pair of conflicting operators. So look at this. T1, there's a write A. T3, there's a read and write A, right? There's conflict, so there's an edge from T1 to T3. If you look at this pair, right? So there's conflict from T2 to T3, from T2 to T1. And then if you look at this, then there's no other conflict anymore in the schedule. And because of this, you can see in this graph, there's no loop, right? T2 goes to T1, T1 goes to T3, it never goes back. In this case, right, so this schedule is actually conflict serializable. What is the schedule that is a conflict serializable, like conflict equivalent to, right? In this case, it's equivalent to the schedule from T2, then to T1, then to T3. Okay? Once you know the dependency graph, you can decide whether a schedule is conflict serializable, and also you can decide the schedule that is the conflict equivalent to. Okay? That is how we do this. Okay. So there are 2 claims that we can make. So yeah, sure, like one claim. So a schedule is conflict serializable if and only if its dependency graph is acyclic. There's no loop. Okay? So how can we prove this? So when we go back home, this is something relatively easy to prove. You prove these 2 different directions. You first look at the first direction. That is, if the dependency graph is not acyclic, it's actually not acyclic, then the schedule is not conflict serializable. So the way to deal with it is you imagine a schedule that has essentially like this pattern. You construct a loop, and you try to prove that there's no way this schedule is conflict serializable because you cannot swipe it. And you prove the other direction. That is, if the dependency graph is acyclic, then the schedule is conflict serializable. So the way to think about it is you do induction by the number of nodes in the dependency graph. You start from a smaller dependency graph that's acyclic. You say, yeah, assuming that is conflict serializable, you add a node, and you try to reason about that. So it should be relatively easy to prove this statement. OK, so we are going to look at more examples once we take a break. Yeah, let's take a break. OK, so let's continue. Can people on Zoom hear me? OK, great. So let's look at this schedule together, right? So we have these 3 different transactions. Is this one conflict serializable? Well, and the way to look at it, right, so you look at every single pair of operators that are conflicting with each other. And then you construct dependency graph. So assuming you look at this pair, you have T1 and T2, right? They read and write the same object, right? So there's a conflict. The instruction in T1 happens earlier, so in the dependency graph, you have the edge from T1 to T2. And then if you look at this pair, right, there's conflicts. T2 happened earlier, so you have an edge from T2 to T1, right? So at this moment, you are done, right? So there's already a loop in the graph, so this one cannot be conflict serializable. But you can continue this exercise until you have the full graph, right? Here you have T2 to T3, right? You have something like this. If you look at this pair, right, you have T1 to T3. So this is the full dependency graph. As you can see, there's a loop, right? So this one is not conflict serializable. But another thing that kind of interesting is we know this one is not conflict serializable because there's a loop in the graph. But is this one serializable? That actually becomes a little bit interesting. Is this one serializable? In this case, it is. Why? Because it actually have the same effect as if, because it keeps overwriting stuff, right? At the end of the day, what you have is the state from T3. If that is the case, it is equivalent in the result as if you run T1, you run T2, then you run T3, because it doesn't matter what T1 and T2 has. The only thing these 3 transactions going to do is the last write A from T3. So this is one schedule that's actually serializable, but not conflict serializable. By only look at the I/O pattern, we are essentially saying that for all the possible compute, for all the possible database instance, this thing is going to be serializable. That's intuitively what we want from conflict serializability. So it's much stronger than serializability. And this is the relationship, right? If you look at all the possible schedules, right, there's all the schedules. Some of them are serializable, some of them are conflict serializable, and some of them are zero schedule. Okay, so this is the relationship. So now we understand the notion of conflict serializability. We understand the property we want to enforce for a transaction. Now let's talk about how to actually enforce it. How can we generate a schedule that's conflict serializable? So inside the database, there is another layer in the system that we haven't talked about yet, which is essentially a scheduler. The job of scheduler is to issue operations to the database engine such that the schedule you are going to have is conflict serializable. So how can we enforce that? There are actually 2 different views about how to enforce conflict serializability. So it depends on whether you are taking an optimistic view or whether you are taking a pessimistic view. So what do we mean by this? You could think about conflicts or just non-serializable behavior as something that will happen all the time. That could be your basic assumption. That is, if I do nothing, there will be conflict all the time. So essentially, if you take that view, the best thing you can do is to prevent those conflicts from happening. You proactively do that if you take a pessimistic view. If you take an optimistic view, you are actually saying, okay, I know there will be conflict, but those conflicts are very rare event. Maybe I run the whole transaction for a day, there's one conflict. If you take that view, right, one way to deal with that is I do not proactively prevent that from happening. I just let everything run, and then I will check, I will deal with it when that happens. So depending on your assumption on how often this non-serializable behavior going to happen in your workload, you have these two very different ways about how to enforce serializability. Now let's look at one example, right? So in the very beginning of booking all those vaccines, right? So why do you see this thing, right? Whenever you click, okay, commit, right? And they'll say, yes, your slot is already booked by other people. What is the fundamental assumption the system is making? Essentially, what the system is trying to do is, I assume there's no conflict. Everyone just book their slot, and you click confirm, and then I check. When two people are booking the same slot, then I deal with it. Essentially, underneath the cover, when you see something like this, the system is taking a very optimistic view about your workload. That is, it's very rare that two people book the same slot. That is the underlying assumption. Again, assumption can be wrong, but this is the assumption. Given that assumption, you have the system design. But you could also take a pessimistic view. That is, whenever I'm booking something, right, you will not let me to proceed. Whenever I kind of book a slot, then all the other users going to wait. In that case, you will never roll back any of the user. Everyone just wait, right? When someone finishes the booking, then another user comes in. If you take a very pessimistic view of the workload, that is, non-serializable behavior going to happen all the time, sometimes you just let other people wait instead of deal with it, because you need to deal with it all the time. So today, we are going to take a pessimistic view. We are going to think about how to proactively prevent non-serializable behavior from happening. And next week, we are going to take an optimistic view. We are going to let everyone run, and then we check when they want to commit. Okay? So the way to take a pessimistic view, one way to do that is by holding locks. So high-level idea is that before you can do anything, you need to acquire a lock such that other transactions knows you are using this object. Okay? So one basic assumption that we are going to make is when you run a transaction, because we always show the full schedule, right? So that might give you an impression that you know the full schedule when you make a decision. But one assumption we are going to make, which is actually often the case in practice, is you do not know about the future. Okay? So you only know what happened so far in the transaction. You will never see the future. Okay? Whenever you are trying to make a schedule, you need to make sure whatever happens in the future is going to be fun. Okay? You do not see the full schedule. The high-level idea is before the system accepts data X, it needs to lock X such as other transaction cannot access it at the same time. And the system only release the lock only when it's safe to do so, which means that execution will be guaranteed to be conflict serializable. If you look at this really natural idea, there are two fundamental questions we need to understand. The first one is when to acquire lock, and second is when to release locks. For different answer of these two questions, you have different locking strategy, which give you different performance in terms of speed and also different guarantee on serializability. Now let's look at one example. So here we have this lock manager, which essentially try to keep track of all the locks in the system. And we have these two special statements. One is lock, and another is unlock. So if you run this schedule, right, essentially in the beginning, T1 is going to acquire lock from the lock manager, and lock manager will say, okay, I grant this lock for T1 on object A. And then T1 can read it, okay? And then T2 will also try to lock A. In this case, the lock manager, because some other transactions is holding the lock on the same object, the lock manager will say, okay, I do not give you lock. And in this case, the behavioral system is T2 going to wait until the lock manager can actually grant the lock. And in the meantime, T1 going to proceed. T1 going to continue to write A, read A, do whatever it wants, and then it unlock A, release the lock. And the lock manager will say, okay, yeah, T1 release the lock, and then tell T2, I can now give you a lock on A. And then T2 proceed. Read A, write A, unlock A, and both commit. Make sense? This is what we are expecting from lock and unlock, these two instructions. So we can use locking to enforce serializability, right? So in this example, if you think about what locks is trying to do, it's actually try to enforce all the conflicts happen from one transaction to the other. It's actually enforcing the direction of conflicts. In this case, because T2 need to wait, all the read and write conflict on object A will all happen from T1 to T2. It is actually not possible for there's a conflict from T2 to T1. It's because of the lock. T2 always read and write A after T1. And that is a high-level idea that we are trying to do. We are trying to use locks to enforce all the conflicts happen in the same direction. And because of that, if you construct a dependency graph of this, it will not have a loop. That is at a high level what we are actually trying to do. But on the other hand, so there are different type of locks. So different type of strategy that you can do. So here we talk about two different strategies. The first one is called two-phase locking. The second one is called strict two-phase locking. We are going to talk about deadlocks and so on and so forth. We are going to talk about granularity of locks, other type of things. So there are different type of locks. Okay. So here we talk about two very simple type of locks. The first one is called share lock, which is the thing that you acquire when you want to read something, called share lock. And second is called exclusive lock, the write lock. Is you acquire this before you want to write something. Okay, so there are these two different level of locks. So when you read something, you need a share lock. When you write something, you need a exclusive lock. The intuition is, if all the operations are read operations, and they can just run, do whatever they want. So read need a much weaker notion of locks than write. And then we want to decouple this. So this is the compatibility matrix, right? So assuming in the system there's three possible states. There's no lock on the objects. You read horizontal way. There's no lock on the objects. There's a share lock on the object, or there's exclusive lock on the object. So assuming that there's no one holding the lock, and someone acquire a share lock, the system is going to grant it. Okay? And then on the other hand, when someone is holding the share lock, and some other people try to acquire another share lock, the system is going to grant it because two transactions can read the same thing together. Okay? So it's fine. When someone is holding the exclusive lock and someone try to acquire a share lock, it's going to deny it. Okay, the share lock going to wait. Similar for the exclusive one, right? So essentially, when someone is holding a share lock, someone else acquire exclusive lock, it's going to wait. Someone holding exclusive lock and another person acquire exclusive lock is going to wait. So this is a compatibility matrix of locks. So we have these two different type of locks. So why use different type of locks? Because you want to actually increase concurrency, right? You want to make sure two threads can actually read the same thing together because there's no conflict. So this is actually something quite special for database in operating system, right? So sometimes you have one type of lock, right? So the only reason that database can actually do a little bit more is that we actually know the semantics of operations. We actually know what we are actually trying to do. And on the other hand, for operating systems, sometimes you need to make a worst-case assumption on what you are trying to do. All the operations essentially are a whole bunch of black boxes. It's very similar to buffer manager, right? In database, because we know, yeah, that's a SQL query I'm trying to run. I actually know more information compared with your operating system. So in practice, there's a whole bunch of different type of logs, right? So there are a lot of optimization and tricks that you can do. We're not going to talk about it in the course. So one thing that's very important is to go back to two fundamental questions: when to acquire log and when to release log. It may sound very trivial, but not all the logging strategy can give you a conflict serializable schedule. It's not like you can just log and log as you wish. Let's look at one example. So assuming I have these two transactions, okay? In the beginning, T1 is going to ask for exclusive log on A, because I know I'm going to write it. Okay? And then T2 will say, I will also write A, but I want a log. So in this case, the log manager is going to ask T2 to wait, because someone else is holding the exclusive log. And then T1 do things on A. It read and write, and then I'm done. I'm not using this anymore, right? So I will unlock A, and then T2 get the log. Then T2 can proceed. T2 write A, and then T1 say, yeah, wait, I actually want to read A again. I want another log from A, because T2 is holding this log. T1 need to wait, and then T2 do whatever, unlock A. T1 get the log, read A, and unlock A, both commit. This is reasonable, right? This essentially says, before I use this object, I lock, and after I use it, I unlock. And then if I want to use it again, I acquire another lock, and then finish using it and unlock it. Is this okay? Will this give you something conflict serializable? This locking strategy is a very natural one. So let's look at this, right? If you look at these two pairs, in a dependency graph, you have the edge from T1 to T2. If you look at this pair, in the dependency graph, you have the edge from T2 to T1. So this thing is not conflict serializable. Even your read and write are both protected by logs. So there's something we need to do about logging strategy, because not all the logging strategy will enforce serializability. One way to enforce that is by doing something called two-phase locking, which works as the following. It's actually partition the transaction into two different phases. So first phase is the growing phase. In this phase, you can only acquire logs. Okay? You cannot release logs. And then in the second phase, it's a shrinking phase, where the transaction can only release logs but not acquire logs. Make sense? You cannot acquire log, release log, and acquire again, because all the acquisition of logs need to happen in phase one, and after that, you can only release logs. If you think about the number of logs a transaction going to hold, it's going to look like this. The x-axis is time. The y-axis is actually number of logs transactions holding. It's going to grow, and it can acquire more and more logs, do whatever, and release them. Okay? If you have this schedule, you're actually following this two-phase locking schedule. So this is one example. In this example, right, so T1 is going to say, I'm going to do something on A, I'm going to acquire a lock manager is going to give it. T2 also do something on A, but the lock manager will ask it to wait. And then T1 is going to do whatever, and then unlock A. Once T1 unlock any logs, okay, it cannot acquire logs anymore. Okay? So the first unlock statement from T1 is the last time T1 can acquire any logs on any object. Okay? So then T1 is going to unlock A, right? T2 get the lock, write whatever, unlock A, and both commit. If you look at this, right, because I release locks toward the end, all the conflicts will be from T1 to T2. So that order is being enforced. So that is why, like this is going to give you conflict serializable schedule. So this is a claim, right? Two-phase locking, if you follow that schedule, guarantees conflict serializability. It only generates schedules whose dependency graph is acyclic. If you small y, so think about all the conflicts of the same object A. It will be from T1 to T2 if T1 acquire locks earlier than T2. So if on A, there's from T1 to T2, and on B, there's T2 to T1, that's not possible. Because there's no way T2 can start doing things before T1 release the lock. And once T1 release the lock, it cannot acquire locks anymore, so it cannot do anything on B. So because you have this growing and shrinking phase, this case is not possible. You cannot have one object where the conflict is from T1 to T2. You have another object where the conflict is from T2 to T1. That's simply not possible. Because that's not possible, all the schedules that you are going to allow in two-phase locking is going to be conflict serializable because dependency graph will not have a loop. That's a high-level idea. So two-phase locking is not perfect. It has a whole bunch of problems. Some of them are not related to isolation, actually. Now let's look at this problem. It's called cascading abort. Assuming I have these two transactions. Here, I have T1 ask for lock of A, T2 ask for lock of A, T1 get lucky, system gave T1 the lock, T1 do things, unlock A, then T2 get the lock, do whatever, then T1 abort. What would happen in this case? First one, this schedule is allowed under two-phase locking. There's nothing wrong. I mean, if you do two-phase locking, you are able to have this schedule, right? You grow, you shrink. It's just between I unlock A, between that and I abort, I release lock A and T2 do things. T1 abort. In this case, what should I do? I have to abort T1. I don't have a choice there. It's not say, yeah, you ask me to abort T1, I don't. No. I have to abort T1. I need to roll it back. But because I roll back T1, T2 is actually reading something that doesn't really exist. Because T2 is reading the result from T1. In this case, if I abort T1, I also need to abort T2. Because T2 is relies on a wrong result, like on a wrong value of the objects. Okay? So that could cause problem. It's not because it's going to be slow. First, it is going to be very slow because you are going to have this cascading abort behavior. But what's become even worse is what if T2 commit before T1 abort? That also could happen, right? So nothing stopped me from doing this. This actually gets worse because now T2 commit. And I told the user it's committed, and now you want me to abort T1. There's nothing I can do. I mean, what can I do? The only thing I can do is to tell the user, okay, I told you T2 committed, but no, I need to abort your committed transaction. Because the computation you are doing relies on transaction that I have to abort. This will not give you durability. It gives you isolation. Could be, but it doesn't give you durability. So, of course, if you look at this, we need to do something about two-phase locking. Because even though it gives you a schedule that is conflict serializable, it cannot fully implement these four properties we want from a transaction. So what can we do? An alternative way of doing this is by doing something called strict two-phase locking. The meaning of the word strict will become very clear next week. There's a very precise definition about what is strict. But so far, just trust me, this thing is called strict two-phase locking. Again, it's two-phase locking, right? It partitions the whole thing into two different phases. So first phase is the growing phase. It's the same. So first phase is the growing phase. Each transaction acquires locks, and it cannot release lock in the first phase. It is a phase 2 that's different. In strict two-phase locking, you are going to hold all the locks until the very end of this transaction. Okay? If you compare that with two-phase locking, right? So in two-phase locking, after phase 1, I'm allowed to release my lock gradually. Okay? In strict two-phase locking, all the locks, I need to hold them until the very end. Very end means commit or abort. Okay? Before that, I have all the locks. If you look at the number of locks you have in strict two-phase locking for each of those transactions, you see this growing phase. Okay? The number of locks that this transaction have monotonically increase. And then it doesn't change anymore after phase 1. Toward the end of the transaction, suddenly I release all the locks. Okay? This is strict two-phase locking. So we can put this side by side. If I do two-phase locking, right, I'm able to have this behavior. I'm able to have this gap in transaction 1 between unlock and abort. There's a gap here. Other transactions can do things in the middle. And that causes the cascading abort problem, because I don't know what other things like other transactions are going to do in the middle, and the other transaction could read something and commit, and then there's nothing else I can do. If you do strict two-phase locking, and if you look at these two instructions, unlock and abort, there's no gap in the middle. Okay? Nothing can happen in the middle, because I only release my lock toward the very end of this transaction. These two things happen together. Nothing can happen in the middle. That is how we avoid this cascading abort problem. Make sense? Because T2 only gets the lock once T1 is done. Okay? That is the behavior we want to enforce from strict two-phase locking. Make sense? Okay. Now let's look at this schedule. So first question that we want to understand is that if you look at two-phase locking, not strict two-phase locking, two-phase locking, can we generate this schedule? Is this schedule possible under two-phase locking? I don't know the answer. We need to look at them together. Okay? T1 want to get a lock, and being lucky and get it. Read A. In the meantime, T2 want the lock, into wait. T1 do things, write A, unlock A. T2 do something, do B, then T1 acquire lock on B. Who thinks this is possible under two-phase locking? Who thinks this is not possible under two-phase locking? So this is not possible because I cannot acquire a new lock after I start to release locks. Okay? This is not possible under two-phase locking. It is possible under strict two-phase locking? Of course not. Right? Strict two-phase locking even, more restrictive. The strict doesn't mean it's more restrictive. It means a different, very precise thing. So strict two-phase locking only allows a subset of schedule compared with two-phase locking. What about this schedule? It is possible under two-phase locking. T1 has exclusive of A, and then acquire another lock on B, unlock A, unlock B, commit. Okay? T2 acquire lock on A, acquire lock on B, unlock B, unlock A, do something, commit. Is this possible under two-phase locking? Who thinks it's possible? Who think is not possible? This is possible, right? Because T1 has growing phase and then shrinking phase. T2 is the same, growing, shrinking. What about strict two-phase locking? Can strict two-phase locking give you this? No, right? Because I have this. After I unlock A, T2 does something else. That's not possible. In strict two-phase locking, I need to hold all my locks toward the very end of this transaction. So this is not possible under strict two-phase locking, but possible under two-phase locking. What about this one? Pretty much same as before. The only difference is T2 would start to hold locks, print A plus B first, then unlock all the objects, then commit. Possible under two-phase locking? I think who agree? Okay. Possible under strict two-phase locking? We agree? Yes. That's the difference. Make sense? So this is the difference between these two locking strategies. But two-phase locking is also not perfect. There could be problem coming from strict two-phase locking also. Now let's look at this schedule. We have T1 have exclusive lock, T2 exclusive lock on B, different objects, okay? T1 holding lock on A, T2 holding lock on B. Different objects, it's fine. T2 read A, T1 read A, whatever. Then T1 acquire lock on B. And then T2 acquire lock on A. What would happen? First one, like, is this allowed under strict two-phase locking? It is allowed, right? And nothing wrong, right? T1 keep acquiring locks, T2 keep acquiring locks. They are both growing. There's nothing wrong with this. But what's the problem? If you look at this schedule, right? At this moment, when T2 acquire lock on A, it need to wait for T1 because T1 is holding the lock. And at this point, when T1 try to acquire lock on B, it also need wait for T2 because T2 is holding the lock. So essentially at this point, they are waiting for each other and no one can make any progress because there's deadlocks. When you implement strict two-phase locking, you could have deadlocks. And also two-phase locking, you could also have deadlocks, right? So you could have deadlocks in strict two-phase locking, that none of those transactions are able to make any progress. So how can we do that? First one, we need to detect it to see whether there is deadlock in the system. The second, we need to resolve it. Whenever we see there's deadlock, we need to think about what to do. So for detection, as you can imagine, it's kind of relatively natural to detect, right? You construct a graph. Each node is a transaction. And then if there's an edge from T1 to Tj, if, for example, Ti is waiting for Tj. And then the system has deadlock if this graph is not acyclic. So for example, your system is like this. This is your current kind of like which transaction is waiting for like which one. In this case, right, so T1 waits for T2, right? So there's an edge from T1 to T2. T2 waits for T3. There's a one from T2 to T3. You continue to do this exercise, you have this graph. So it's very natural to see, as long as there's a loop in the graph, there's a deadlock, right? Because all the transactions in the loop cannot make progress. They are waiting for each other, okay? So detection is relatively easy. In the system, whenever you register a lock, you could do this exercise automatically in the system side. So similarly, if you look at this example, right, you will have this waitful graph look like this. T1 waits for T2, T2 waits for T1. There's a loop, so there's a deadlock. That's how this deadlock shows up in the graph. The second question is, if I know there's deadlock in the system, how can I handle it? The handling of deadlocks is kind of interesting. There are actually a whole bunch of things you can do. One thing that you can do is that you just roll things back. Okay? You have a loop. You kill one of the transactions. You issue the abort statement for one transaction, not by the user, but by the system automatically. When you design such a system, there are multiple things that multiple design decisions you need to make. The first one is, okay, I need to check deadlocks. How frequent should database detect deadlocks, right? How often should I actually construct the waitful graph? Well, for this one, there's a whole bunch of things you can do, right? You can maintain this waitful graph every single, like whenever you issue a lock. But you can say, yeah, I allow you to have deadlock up to 1 second, right? In that case, every single second, right, you construct this waitful graph. Depending on what you want to do, depending on your assumption on how often deadlock going to happen. And second thing is, whenever you have a deadlock, the question is, I have a whole bunch of transactions in the loop. I need to break the loop, so I need to kill someone. Which one should I kill? Which transaction should I abort? So you could have a whole bunch of things. You could say, I mean, this is actually very interesting because it's not really clear which one should do. We could kill transaction by age, right? We could say there's one transaction being running for a day now, and almost done. There's another transaction started just 1 second, right? In this case, you don't want to kill the old transaction. That one have done a whole bunch of things, right? So you want to maybe kill the new one, right? To say, yeah, I mean, you haven't made too much progress yet, right? So I abort you, and you try again. Right? You are not wasting a whole bunch of resources. But it's not clear that's always a good option, right? Because there could be the case that you have a very old transaction. The transaction is old because it keeps waiting for other people, right? In that case, maybe kill that one is more interesting, right? So it's not really clear what to do, but usually, right, in the system side, you may want to consider killing a transaction that haven't made too much progress yet, if you care about resources. The progress is another thing. Age and progress are kind of different. So another thing is the items that the number of logs that this transaction hold. The more logs this transaction hold, the moment you kill it, it's going to release more logs. Potentially, it could break actually more loops in the graph, because there could be more than one loop in the graph. So you might want to consider the number of items that are being locked by this transaction. And also how many deadlocks that they can break by killing this. And also how many rollbacks that you are going to have. Because those transactions have dependencies, right? Once I like abort this transaction, I might need to abort another transaction. Right? There could be all those rollbacks, right? So in this case, you want to consider, right, how many rollbacks I'm going to cause when I kill one of those transactions. So, and also number of times a transaction being aborted in the past. You don't want to keep killing the same transaction again, and again, right? You want to have some fairness about which one to kill. So as you can see, there's a whole bunch of interesting decisions you need to make when you want to pick one transaction to kill. In real system, people pick one very specific point in the space, given their assumption on the workload, okay? And also given the service level agreement they have with the user, okay? So, and this is something you can tune. You can tell the system, okay, I want to do this strategy, I want to do that strategy, this is how I want to resolve the transaction. Okay, so that's all we have for today. We talk about isolation, we define formulae, and we talk about how to enforce it with locking. Next week, we are going to enforce isolations without lock anything. Yeah, I'll see you guys next week.